So we're taking what may seem like a detour to talk about carbohydrates, but it's not going to really be a detour because carbohydrates have tons of oxygens, and we're going to see that we can do acetal and hemiacetal reactions with carbohydrates. So carbohydrates are polyhydroxyaldehydes and ketones. Okay. They are called aldoses or classified as aldoses or ketoses, depending on whether they're aldehydes or ketones that they came from. And they're further classified as hexoses or pentoses based on the number of carbons in them. So a quick little recap of what the heck D and L mean. This is glyceraldehyde, the two enantiomers of glyceraldehyde. Glyceraldehyde only has two enantiomers because there's one asymmetric carbon. So glyceraldehyde can exist as R and as S, and you're going to have to identify which is which. But biochemists talk about D and L rather than R and S. They're related but different. When I draw an aldehyde containing compound like carbohydrates that we'll see in a moment, in a Fisher projection like this, the aldehyde goes up top and there's always a CH2OH that's at the bottom. The H and OH go across the horizontal. If the hydroxide is on the left of your Fisher projection, that's an L glyceraldehyde. If it's on the right, it's D-glyceraldehyde. So we've got L on the left and D on the right of this glyceraldehyde. Well, this is an aldohexose. Why is it an aldohexose? Because there's an aldehyde. It's a hexose because there are 6 carbons. CHO, aldehyde, goes up top, always in a Fisher projection. CH2OH at the bottom of the Fisher projection, every time. When you're trying to designate D and L, you don't look at the whole sequence of carbons. You don't look at every individual OH across the thing. You look only at the bottom OH in your Fisher projection. So this one is D-glucose because that hydroxide is on the right. This is L-glucose because that penultimate hydroxide is on the left. This is glucose. These are enantiomers of glucose. Glucose can exist as the open chain form, but it can also exist as the cyclic form. Let's see a couple of drawings. So this over here on the left is the open chain form of glucose. It's not exactly in a Fisher projection anymore because these heavy wedges are obvious. But if you look, and all of these are heavy wedges across the middle, the way they would be in a Fisher projection, that causes that molecule to sort of bow backwards and coil in on itself. Maybe that's a weird way to say that, but you get something that results like this, where it's a curled molecule. It's not a straight chain molecule at all. So even when glucose is in its open chain form, it can be coiled up like this, just still not connected as a ring. So how do you convert from open chain glucose to closed chain glucose, cyclic glucose? Well, this oxygen down here, the one that helped us designate whether this was D or L glucose, that oxygen is this top oxygen up here that attacks the carbonyl carbon. So that oxygen attacks your carbonyl carbon, makes your carbonyl oxygen an O-, and then this O- that you're going to make can get protonated to become an OH. So that OH could end up pointed down like this or pointed up like this. Both of those molecules are glucose. The only difference is the one on the left we call alpha glucose. The one on the right we call beta glucose. They're both D-glucose because of the yellow highlighted oxygen on the left being on the right of your Fisher projection. So how do you end up forming both up and down? Well, that carbon that you attacked was an sp2 carbon, which means trigonal planar. So when that yellow oxygen attacks, it can attack from the top and send the oxygen backwards, send the oxygen down to make alpha glucose. That yellow oxygen can attack from beneath the carbonyl carbon and send the blue oxygen up, making beta glucose. Anytime you attack an sp2 carbon like that, it could attack one side or the other. Remember carbocations, sp2? It could attack one side or the other. It will do both. So that's why we always get alpha and beta glucose when we close it up like this. Hayworth projections, that's these guys. Remember, those are really biochemistry type drawings. What does an organic chemist like to draw instead? Chair structures. Chair structures are what organic chemists draw. It's the same exact thing. I can highlight the same oxygen in yellow. That's this oxygen. I can highlight the same oxygens in blue. The carbonyl oxygen was the oxygen that became blue. That's this one in alpha glucose. That's this one in beta glucose. Before we wrap up this whole alpha beta glucose business and move on to glycoside bonds, we need to introduce you to two more words, two more terms, stereochemistry terms. These two molecules, alpha and beta glucose, are epimers. What is an epimer? An epimer is a diastereomer, but it's a narrower classification of diastereomers. Remember, diastereomers have at least one the same, at least one different. Diastereomers must have two asymmetric carbons and at least one the same, at least one different. Those two molecules will be diastereomers. Epimers are things that have all the same except one. This alpha glucose and beta glucose, everything is the same except for one carbon. So these could be called epimers, can be, will be called epimers. But these, because they are carbohydrates specifically, are often referred to as anomers. That's an O, anomers. What is an anomer? Anomers are things that differ. Anomers are a classification of epimers, but they differ only at the anomeric carbon. You guessed it. This is the anomeric carbon. This one. Anomeric carbon. The anomeric carbon is officially known as the acetal/hemiacetal carbon. Did you notice that that carbon has a hemiacetal? The hemi part is highlighted in blue. The acetal part is highlighted in yellow. That anomeric carbon is where all of the action happens in all of the carbohydrates we're about to walk through. So we're about to draw some big carbohydrate molecules, but everything's happening at the anomeric carbon. Got it? All right. So I bet you have heard of glycoside bonds. What is a glycoside bond? Well, what happened from my reactant to my product? Identify what's different. Something is different at the anomeric carbon. My anomeric carbon had an OH in the reactant, and it's an OR in the product. I changed my thing from a hemiacetal to an acetal. It changed from a half acetal to a full acetal. Let's draw the mechanism of how that happened. It looks fancy because we're drawing it in a chair structure. It looks fancy because it's a large molecule, a big molecule. But there's really nothing special or fancy about how this reaction works. It's a hemi becoming an acetal. So a hemi becoming an acetal, protonate the oxygen. Which oxygen? The oxygen on the anomeric carbon, because you want one of the oxygens on the anomeric carbon, the OH one, because you want that one to leave. So protonate that one. to make it water connected. Fill in all the remainder of the stuff, and then fold down the other oxygen on your anomeric carbon and kick out your water. It's a little bit wrong to continue drawing it in a chair structure at this point because we have an sp2 carbon here. But I don't think you'll mind. Do you mind? I hope not. I'm going to keep it in this chair structure just so that I don't have to flip it out of a chair and then back into a chair in a moment. I keep it in this chair so that I can then attack the carbonyl carbon. I pointed it down like this. Could I have just as easily pointed it up? I could have. Because the carbon that I attacked was sp2 and trigonal planar. So what I was saying about it's a little bit wrong to draw it here. Does that look like it's really trigonal planar? Does that look like it's 120 bond angle? No. So really, we shouldn't draw it in a chair right here, but it's okay. I will allow it. So this thing, the methanol that attacks can attack from way out here like this, end up out like that. It can come from underneath the bottom and end up down like that. Either way, some base comes to clean up, and I'm going to draw it like it's cleaning up both of them, two different bases, so that I can draw the products. Didn't you miss chair structures? Hasn't it been too long? Just too long. Ugh, that one got uglier than average. Ta-da! So this is called a glycoside because my anomeric carbon is now an acetal. That's what a glycoside bond is. So both of these products are formed, but would you have a guess at which one is most likely the major? This one. Why is this one most likely the major? Oh, it goes back to chair structures. And I should have said this when we were talking about glucose a few minutes ago. This is beta. This is a beta glycoside. This is a alpha glycoside because this goes up in the anomeric position. This goes down in the anomeric position. Alpha goes down, beta goes up. So this is the most stable conformation you can ever get. Why? Everything is equatorial. Because everything is equatorial, the stuff gets as much space as possible. When it's axial, remember there's bad 1,3 diaxial interactions. That's no good. So beta is usually more stable. So we could make glycoside bonds like this with something like methanol, but it's also common / this is what all of our polysaccharides are made out of. When one sugar molecule, one carbohydrate, reacts with another carbohydrate, and the alcohol of another carbohydrate, let's say like this one even, the alcohol of another carbohydrate is what attacks instead of methanol attacking. So you connect one carbohydrate to another carbohydrate to another carbohydrate to another carbohydrate. It's glycoside bonds that are bringing those together every time. Whether those glycoside bonds are made with alpha or beta linkages depends on the enzymes and stuff that brought it together, how it was synthesized exactly, but the structure of the resulting polysaccharide, big giant sugar molecule, the structure of the resulting polysaccharide is dependent on whether it's alpha or beta linkages. For instance, Starch and cellulose have very similar makeups, very similar sugar structures, but one has alpha linkages, one has beta linkages, and one is rigid and one is pliable. Check it out. So we've now shown you how to make a glycoside. What if you want to hydrolyze a glycoside bond? This is lactose, which is a disaccharide, a combination of glucose and galactose that can be hydrolyzed by enzymes in our bodies for people that are not lactose intolerant. That can be hydrolyzed into separate galactose and glucose molecules. These molecules. You ready to draw how that happens? Let's do it. Rather than skipping to where this one is already drawn, I want to draw it together so that we can explain one thing. This compound looks like there's a CH2 at this point. That is not a CH2. That should be directly connected to the next sugar molecule, like this. But often in textbooks and places where they're trying to make the structures linear to print them in a textbook, they do make kinks in these bonds so that they can make them horizontal rather than vertical. But that's definitely a vertical molecule. So now I keep drawing and I'll bring you back when I'm done. So you may not have wanted to see it, but I drew this guy in the Haworth projection, like biochemists often do, and in the chair structures, like organic chemists often do. My chair structures are fairly ugly, but so are the Haworth. Whoops, get over it. What's the big difference in glucose and galactose? The big difference is this carbon here, this oxygen. In glucose, that has to be an equatorial oxygen. This is glucose on the right. In galactose, that has to be an axial oxygen. Other than that, these are the same. This is beta glucose because that oxygen is pointed up on the anomeric carbon. Yep, you heard me. Anomeric carbon. Anomeric carbon of glucose, that oxygen is pointed up. On the anomeric carbon of galactose, that oxygen is also pointed up. So this is a beta galactose as well. Why do I highlight those two anomeric carbons? Because that's where the interesting stuff happens. We're going to draw hydrolysis of this disaccharide. Hydrolysis means I need to cut this molecule apart. I need to break this glycoside bond in these guys. I'm going to break it from this anomeric carbon. Leave that anomeric carbon alone. This anomeric carbon is an acetal, a hemiacetal, a ketal, a hemiketal, a hydrate. It's an acetal, so we're going to draw acetal hydrolysis. You ready? Since I have identified that that's where my reaction is going to take place, I'm going to draw my mechanism with all of the other stuff ignored. You're welcome. I'm drawing only the part I'm trying to break and the two rings. This is acetal hydrolysis. So protonate the thing you're wanting to leave and then fold it down and kick it out. And all of a sudden, you've got a free glucose. It doesn't look like glucose anymore because I left all of the other stuff off of it. But you've got a free-floating glucose and a free-floating galactose. Doesn't look like galactose anymore because all the stuff is off of it. But from here, water attacks the carbonyl carbon. Like that. Some base cleans up to give me this thing in pink. I will officially put my groups back just so that it's a complete structure. And my glucose is also free. I'm going to put it over here as well, and I'm going to put all of its bits and bobs back as well, just for clarity's sake. So this is glucose, that's black. This is galactose, that's pink. Did I make beta galactose or alpha galactose? The one I drew is alpha galactose because my O came in from the bottom and made the alpha galactose. Do you think that water will exclusively attack this way and make alpha galactose? No, it will also make beta galactose. So alpha and beta galactose come from the hydrolysis here, but only beta glucose. Why only beta glucose? Because you started with beta glucose. Did we do a reaction at that anomeric carbon? No, we were trying to hydrolyze my sugar, trying to break my disaccharide, lactose, down into its monosaccharide components. Hydrolysis of an acetal is all we did, no matter how big and fancy it looked. That's enough for now.